should you handle that? Consider preemption while in kernel mode. I think in the previous chapter, we did say that writing operating systems that cannot be preempted is very good. Doesn't lead to deadlocks or critical sections in your code. Very, very safe, but it's always not really responsive because you cannot interrupt the operating system process cannot interrupt themselves. And consider interrupts occurring during crucial OS activities. That's all where we get deadlocks, potential deadlocks, or potential areas of critical code. So the whole mutual flags, semaphores, those kind of stuff. That's where that comes. Next. The last component is this module, what we call the dispatcher. So we've got the first thing that we want to expect you guys to understand the principle of preemption, non-preemption. Sorry, that. CPU bursts and IO cycles. Next thing was the scheduler. Is that how do we select the new processes? Some of them, when do we select? Some of them are when the process itself voluntarily lets go of the CPU. Other times when it's an involuntary switching away. And the last thing is the role of the dispatcher. So the dispatcher is like the brother of the scheduler. And the dispatcher is responsible for this context switching that must occur from the running process to the new running process. It controls the CPU to the process selected. It must switch the context, switching to user mode potentially, and it jumps to the proper location in the user program to restart the program. So that's the role of the dispatcher. And you want to make sure that the dispatcher, the code of the dispatcher itself, is as fast as possible, meaning as little time should be spent during the dispatch period. That's what they call dispatch latency. If you spend a lot of CPU cycles handling this context switching, getting the process to run, then you're wasting unnecessary CPU time. So very effective operating systems try to make this code extremely efficient, obviously, and the schedulers themselves. So schedulers shouldn't spend a lot of time selecting which one should be selected. The same with the dispatcher itself. So there's a number of criteria that we can use to evaluate scheduling algorithms. And in most cases, you cannot just use one of these criteria. We have to take into consideration the CPU utilization. We want to make sure that we keep the CPU as busy as possible so that we don't waste enough CPU time. Throughput is the number of processes that completes their execution per time unit. The more processes potentially you can have, the more positive it potentially can be. There's also what we call turnaround time and waiting time. Turnaround time is the amount of time to execute a particular process. Waiting time is the amount of time a process has been waiting in the ready queue before they can run. And you see a lot of the examples in the textbook describes that for certain algorithms, why it's more efficient to order your process in such a way to keep your waiting time, your average waiting time as short as possible. And then you also have what they call response times. That is the amount of time it takes from when a request was submitted until the first response is produced. Until time sharing, basically how quickly can you get this whole time sharing thing going, selecting a new process, interrupting it, and getting a new process running. So here's just how you would measure that. We want max CPU utilization, max minimum turnaround time, minimum waiting time, and minimum response time. And for this, we're moving away back to Excel. Right, so let's have a look. And this is typically what you can expect in exams and semester tests and so on as well. Right, so the first algorithm that we want to talk about is the first come, first serve algorithm. Very, very simple. This algorithm is based on a non-preemptive environment. Now, what does that mean? Basically means that there's no such thing as a flood. Right? Basically, when the process runs, it voluntarily gives up the CPU time. Maybe it's going into the waiting state, or the process terminates. That's typically when the scheduler runs. So in this case, we have a situation, this is just an example of 3 processes. Process A, B, and C. Zoom in a little bit. An important aspect that we have to take into consideration for first come, first served is basically who arrived first. So for this case, we have an arrival time values, where 0 basically means that one arrived at 0 milliseconds, 1 maybe at 1 millisecond, 2 at 2 milliseconds. That's immaterial what the actual unit is. Hopefully you understand then that 0 was the first one, 1 is the second one. So think of it as a queue of the processes coming in. And then we've got our CPU burst time, 24, 3, and 3. So first come, first serve, really simple. Our criteria, whoever is in front of the queue, that's the one we select. So which one arrived first? A, really easy. So typically, in this case, we will have a diagram. The textbook, so just a note of the textbook uses what they call Gantt charts. Now, for those that don't know, a Gantt chart explains the time that passes from point X, from time X, to time Y, from time Y to time Z, and so on and so on. And these times in the textbook describes what they call waiting times. That's good. What we rather want to use in this case is more an explanation of how long it takes for a process to execute while it's loaded in the CPU. So the first one that is running is process A, starts running. And how long does it take for it to run? Remember, this is non-voluntary. This is basically non-preemptive. So it takes the full CPU burst cycle, which is 24. It runs for 24, whatever cycles, milliseconds, nanoseconds, whatever seconds. Next one is B. How long does it run? 3. Then C. 3. Okay. Very, very simple. This is a fairly bad algorithm. Think of it this way. You guys have gone shopping, I hope. And you've seen certain shop, like Checkers or ShopRite or whatever, there's different arrangements in which they can have the tills. One of the arrangements is where they have one long queue, and then you stand at one point, and then there's a bunch of tills. And the first one that opens up, that's the one that you can get to. Guys, got that? Another arrangement is you've got a bunch of tills, but you basically queue behind the till. Now think of this way. Think of the till as the CPU, so there's one till, and you've got a bunch of people queuing. Imagine you see a till opening up, and you run to that till, and just before you got there, someone jumps the queue in front of you. That person has a trolley, 2 trolleys, full of stuff, and you're just behind him with your one little item. 24 milliseconds versus the 3 milliseconds. Your waiting time to be serviced by the till is significant. You wait. Finally, when you get there, it will go quick. If it was a situation where we could say, listen, you, Mr. with the many milliseconds, we can rather get those customers with the shorter groceries first through the till, then potentially it might be more efficient. However, there's issues with that as well, but first understand that first come, first serve, not efficient at all, because of the average waiting time is really, really long that people are going to need to wait, even processes to wait for it to execute. The next one is the shortest job first process. Now, in this case, this is also in a non-preemptible situation. However, This is more realistic to a mainframe environment. So we've got a bunch of jobs